You think you know why salt melts ice. Everyone does. You've seen it happen. Winter comes. The roads freeze. Someone scatters salt across the pavement. The ice disappears. The explanation follows immediately, confidently, casually. Salt melts ice. You learned it in school. You've repeated it yourself. It is one of those facts that sits so comfortably in the mind that it never gets questioned. But here is the problem. That explanation is not an explanation. It is a label. It describes what appears to happen without touching what actually happens. And what actually happens is so different from the story you were told that the moment you see it clearly, you will not be able to look at a frozen surface the same way again. Salt does not melt ice, not in the way you think, not through any process that deserves the word melting in the way you use it. What salt actually does is something quieter, more precise, and more revealing about the nature of matter than any simple story of melting could suggest. It disrupts an equilibrium. It interferes with a process that is already happening, invisibly, continuously, at the surface of every piece of ice that has ever existed. To understand what salt does, you first have to understand what ice is doing when salt is nowhere near it. And what ice is doing, even when nothing is touching it, even when the temperature is stable, even when the surface looks completely still, is deeply counterintuitive. Ice is not sitting still. It never sits still, not even at temperatures well below zero. Start with a piece of ice at exactly 0 degrees Celsius, the freezing point, the temperature at which you were told water freezes and ice melts, the boundary between states. Now look at the surface of that ice at the molecular level. What you find is not a static arrangement of water molecules locked in a crystal lattice. What you find is a constant, furious exchange. Water molecules at the surface of the ice are continuously breaking free from the crystal structure and entering the liquid state. At the same moment, water molecules from the liquid layer are continuously rejoining the crystal lattice and becoming ice again. This is happening simultaneously, continuously, at every point on the surface, all the time. At 0 degrees Celsius, these two processes, melting and freezing, occur at exactly the same rate. For every molecule that escapes the lattice, one returns. The net effect is 0. The boundary between ice and water does not move. The ice does not grow. The ice does not shrink. The system is in balance. This is called dynamic equilibrium. And the word dynamic is doing enormous work in that phrase. The equilibrium is not static. It is not a frozen piece. It is a constant battle that happens to be perfectly tied. The surface is not resting. It is churning, molecule by molecule, at a rate of exchange that if you could see it would look like continuous violent flux. Molecules leaving, molecules arriving. The boundary held not by stillness but by the exact cancellation of two opposing processes. This is the state of ice before salt arrives. This is what you are interfering with when you pour salt on a frozen surface. And the interference is not what you were told. Before going further, there is something else about the ice surface that most explanations leave out entirely. Something discovered in the 19th century by one of the most important experimental physicists who ever lived, and then largely forgotten by popular science. In 1842, Michael Faraday, who gave the world the foundations of electromagnetism, was studying ice. He noticed something strange. When two pieces of ice were pressed together, even at temperatures below 0, they fused. Not because the ice melted under pressure and then refroze. That explanation, which came later and was widely accepted, turns out to be wrong for most cases. Faraday proposed something different. He suggested that the surface of ice, even at temperatures below its bulk freezing point, is covered by a thin layer of molecules that are not quite solid and not quite liquid, a quasi-liquid layer, a transitional zone at the boundary of the crystal, where the molecules have lost the full rigidity of the lattice but have not fully entered the liquid state. Faraday was dismissed at the time. The technology to verify his claim did not exist. It took more than a century and a half, and the development of modern surface physics to confirm that he was correct. The surface of ice is not ice in the way the bulk is ice. It is a region of structural disorder, a few molecules thick, where the crystal lattice frays at its boundary with the world. The molecules there are more mobile, more loosely bound, more responsive to external influences than the molecules deeper in the lattice. This surface layer is not a curiosity. It is where everything that matters about ice's interaction with the world actually happens. It is where dynamic equilibrium plays out. It is where salt exerts its influence. It is, in a very real sense, the most important part of the ice, and it is the part that almost no one mentions when they explain why salt melts ice. Now bring the salt. You pour sodium chloride, table salt, onto the surface of ice. What happens? The first thing that happens is that the salt dissolves, not into the bulk ice, into the quasi-liquid layer on the surface. That thin, disordered boundary region contains enough mobile water molecules to begin dissolving the salt crystals. Sodium chloride dissociates into sodium ions and chloride ions, and those ions distribute themselves through the surface liquid layer. Now the surface is no longer pure water. It is a salt solution. Dilute initially, but a solution. Here is where the common explanation goes wrong. The common explanation says that salt lowers the freezing point of water, and therefore the ice melts. This is technically true, but mechanistically misleading. It makes it sound as though the salt reaches into the ice and pulls molecules free, as though it actively causes melting, as though melting is something the salt initiates. It does not. Melting was already happening. Continuously, before the salt arrived, what the salt changes is not the rate of melting. What it changes is the rate of freezing. Follow this carefully, because this is the actual mechanism. In the dynamic equilibrium at the surface of pure ice at 0 degrees, water molecules leave the lattice and enter the liquid phase at a certain rate, and water molecules from the liquid phase rejoin the lattice at the same rate. Balance, equilibrium, no net change. Now introduce ions into the surface liquid. Sodium ions and chloride ions, electrically charged particles, distributed through the water. These ions interact with water molecules. They form hydration shells. Each ion surrounds itself with water molecules that are electrically attracted to it, organized around it, partially bound to it. Those water molecules are no longer free. They are engaged with the ions. They are not available to rejoin the ice lattice. And here is the consequence. The rate at which water molecules return to the lattice, the rate of freezing, decreases. Not because the temperature changed, not because some new energy was added to the system, but because the ions have reduced the concentration of free water molecules available to crystallize. The rate of melting, molecules escaping the lattice into the liquid, remains the same. The lattice does not know about the ions. The crystal structure at the surface continues releasing molecules at the same rate as before, but the rate of freezing has dropped. Melting rate unchanged, freezing rate reduced. The equilibrium is broken. The balance tips. More molecules leave the lattice than return to it. Net ice loss. The boundary moves. The ice shrinks. This is what salt does. It does not melt ice. It prevents refreezing. It disrupts the return side of the dynamic equilibrium. The ice melts not because something is added to it, but because something is subtracted from the opposing process. The distinction matters because it changes everything about how you understand what is happening at that surface. There is a principle in chemistry that describes what happens when you disturb an equilibrium. It was formulated by Henri-Louis Le Chatelier in 1884, and it applies to every system in dynamic balance. Le Chatelier's principle states that if you disturb a system in equilibrium, the system will shift in a direction that opposes the disturbance and restores balance. Apply this to the ice surface. The equilibrium is between melting and freezing. You introduce ions. The ions reduce the freezing rate. The system is now out of balance. Le Chatelier's principle predicts that the system will shift to oppose this. And the only way to oppose the reduction in freezing rate is to melt more ice, to produce more liquid water, which dilutes the ion concentration, which eventually allows the freezing rate to recover. But here is the thing. The system reaches a new equilibrium only at a lower temperature than 0 degrees Celsius. A temperature at which the concentration of ions in the solution is high enough that the reduced freezing rate matches the melting rate again. That temperature is lower than the original freezing point of pure water. This is freezing point depression, and it is a colligative property, meaning it depends not on what the ions are, but on how many of them are present. More ions, more depression of the freezing point. The identity of the salt matters less than the number of particles it contributes to the solution. Sodium chloride dissociates into 2 ions per formula unit, 1 sodium, 1 chloride, so each dissolved unit of salt contributes 2 particles to the solution. This makes it moderately effective at depressing the freezing point. Other salts that dissociate into more ions would be more effective per unit mass. The magnitude of the freezing point depression follows a precise mathematical relationship. For a dilute solution, the depression is proportional to the concentration of dissolved particles. The proportionality constant for water, called the cryoscopic constant, is 1.86 degrees Celsius per mole of particles per kilogram of water. This is not approximate. This is law. It follows from the thermodynamics of solutions with the same precision and generality as any other physical principle. It does not depend on the specific chemical interactions between the ions and the water. It depends only on the thermodynamic effect of dissolved particles on the activity of the solvent, on the reduction in the tendency of water molecules to enter the solid phase. Now consider the eutectic point, because this is where the explanation becomes important, not just intellectually, but practically. Sodium chloride can depress the freezing point of water, but only up to a limit. That limit is determined by how much salt can dissolve in the water available, and by the thermodynamics of the sodium chloride and water system. The eutectic point for sodium chloride and water occurs at approximately negative 21 degrees Celsius, with a salt concentration of about 23% by weight. This is the lowest temperature at which a liquid sodium chloride solution can exist. Below this temperature, no amount of additional salt will depress the freezing point further. The system freezes completely. What this means in practice is that salt is useless on ice when the temperature drops below approximately negative 21 degrees Celsius. Not less effective, useless. The mechanism that makes it work, the disruption of the freezing side of the dynamic equilibrium by dissolved ions, requires liquid water to dissolve into. Below the eutectic temperature, no liquid water forms. The equilibrium cannot be disrupted. The ice remains ice regardless of how much salt you add. This is why road crews in extremely cold climates use different materials. Calcium chloride, which dissociates into 3 ions and has a eutectic point near negative 50 degrees Celsius, works at temperatures where sodium chloride fails completely, not because it is chemically more powerful in some vague sense, but because the number of ions it contributes to solution extends the range over which the freezing point depression mechanism can operate. The eutectic point is not an engineering detail. It is a physical boundary, a line drawn by thermodynamics, and the fact that it exists at all reveals something about the nature of freezing point depression that the simple story of salt melting ice completely conceals. There is something else that happens when you add salt to ice, something that surprises most people when they encounter it for the first time. The system gets colder. Not warmer, colder. You add salt to ice, the ice begins to convert to liquid, and the temperature of the ice-salt mixture drops, sometimes dramatically, well below 0 degrees Celsius. This seems backwards. If ice is melting, shouldn't the temperature be rising? No, because melting is an endothermic process. It requires energy. When the dynamic equilibrium shifts toward net melting, when more molecules are leaving the lattice than returning to it, those molecules must absorb energy to make the transition from the ordered solid phase to the disordered liquid phase. That energy has to come from somewhere. And in the absence of an external heat source, it comes from the thermal energy of the system itself. The ice-salt mixture cools as it melts because the melting process is consuming thermal energy faster than the environment can supply it. This is why ice-salt mixtures have been used for centuries to achieve temperatures well below the freezing point of water without any refrigeration equipment. Pack ice and salt together in a container, surround your substance of interest, and the endothermic melting process will pull the temperature down to near the eutectic point. 17th century confectioners used this method to make ice cream. It is the same physics that underlies modern chemistry cold baths. The temperature drop is not a side effect. It is a direct consequence of the thermodynamics of the phase transition. Energy must be conserved. The transition from solid to liquid requires enthalpy. That enthalpy comes from the surroundings. The surroundings cool. And this is deeply counterintuitive, because the common story, salt melts ice, suggests that something warm is happening, something dissolving, something breaking down. But the reality is the opposite. The process of disrupting the equilibrium and converting ice to liquid solution is a cold process. It draws heat in rather than releasing it. Now step back and look at what you have actually been looking at this entire time. You thought you were looking at a simple everyday phenomenon. Salt on ice, roads cleared in winter, a kitchen trick for making ice cream. Familiar, mundane, fully explained. What you are actually looking at is a window into some of the deepest principles in physical chemistry. Dynamic equilibrium, the continuous exchange at phase boundaries that makes all transitions possible. Colligative properties, the thermodynamic consequences of dissolved particles on solvent behavior, consequences that depend on number rather than identity. Le Chatelier's principle, the tendency of systems in balance to resist perturbation, endothermic phase transitions, the energy cost of moving from order to disorder, the eutectic point, the thermodynamic limit of a two-component system, none of these are exotic. All of them are fundamental, and all of them are invisible in the simple story of salt melting ice. The simple story is not wrong in its outcome. Salt applied to an icy road does result in the disappearance of the ice. The roads do clear. The mechanism produces the effect, but the mechanism is not what the story says it is, and the mechanism matters. Because the mechanism is what connects this familiar phenomenon to every other process in chemistry and physics that involves equilibrium, solutions, and phase transitions. When you understand the mechanism, you understand why salt stops working at very low temperatures. You understand why the road feels colder after salting than before under the right conditions. You understand why different salts have different effective temperature ranges. You understand why the process is self-limiting, why the ice does not disappear instantaneously but converts gradually as the equilibrium shifts and the solution concentration changes. Without the mechanism, you have a fact that works until it doesn't, and no way to know why. There's one more thing worth examining, because it connects to the ice surface in a way that most people never consider. Why is ice slippery? The standard explanation, the one in most textbooks for most of the 20th century, is pressure melting. The weight of a skate blade pressing on the ice creates enough pressure to lower the freezing point slightly, producing a thin film of liquid water that acts as a lubricant. Skaters glide on this film. This explanation is almost entirely wrong. The pressure required to lower the freezing point of water by even 1 degree Celsius is enormous, far beyond what a skate blade exerts on ice. And ice is slippery even when you are not pressing on it. It is slippery to the touch at rest, slippery for objects that exert almost no pressure at all. The actual reason ice is slippery connects directly back to Faraday's quasi-liquid surface layer. The disordered, partially mobile molecules at the ice surface that were confirmed only in recent decades. This layer exists at temperatures well below zero, without any pressure, without any applied force, as a fundamental property of the ice surface. It is this layer, not a pressure-induced melt film, that provides the low friction that makes ice slippery. And just as with the salt story, the true mechanism reveals a connection to broader physics that the false mechanism conceals. The quasi-liquid layer exists because the surface of a crystal is a boundary, and boundaries are disordered. The molecules there have fewer neighbors to bind to. They have more freedom. They are in a different thermodynamic state than the bulk. This is a general principle of surface physics, not a quirk of ice specifically. Every crystalline material has a surface that is different from its bulk. Ice makes this visible because its surface disorder is unusually pronounced at temperatures near its melting point and directly affects everyday experience. The slipperiness of ice is not caused by melting. It is caused by the same structural feature, the same surface disequilibrium, that makes the salt mechanism possible in the first place. You are standing on ice, winter, a frozen surface beneath you. At the interface between your boot and the ice, at the level of molecular structure, what is happening is not stillness, not solidity in any absolute sense. There is a quasi-liquid layer vibrating with partial disorder. Below it, a crystal lattice in constant dynamic exchange with the layer above, releasing molecules and accepting them at rates that define the equilibrium of the system. The temperature, the ion concentration, the pressure, the surface geometry all modulate this exchange, all shift the balance, all move the boundary in one direction or another. When someone pours salt onto that surface, they are not adding heat, they are not chemically attacking the crystal, they are introducing ions into the liquid layer that reduce the rate at which the liquid can return to crystal form. The equilibrium shifts, net melting occurs. The surface converts from solid to solution. The road clears. But the ice was already doing the work, already cycling, already exchanging, already at the boundary between states. The salt did not start the process. It biased an ongoing one. This is not a small distinction. It is the difference between seeing nature as a collection of independent events, salt acts on ice, and seeing it as a field of continuous processes in dynamic balance, systems at equilibrium that respond to perturbation by shifting until they find a new balance. The first picture is simpler. The second picture is true. And the second picture connects this moment, salt on a winter road, to the thermodynamics of every solution, every phase transition, every equilibrium in chemistry and biology, to the dissolution of minerals in groundwater, to the behavior of salt in the ocean and its effect on freezing at the poles, to the preservation of food by salting, to the regulation of ions across cell membranes in every living organism. The mechanism is never isolated. It is always part of a larger structure of physical law that operates at every scale from the molecular to the planetary. You thought you understood why salt melts ice. What you actually had was a story that ended at the surface of the phenomenon without ever going inside, a description of the effect dressed up as an explanation of the cause. The cause is equilibrium, continuous, dynamic, invisible, and far more interesting than melting. The ice was never simply solid. It was never simply waiting to be acted upon. It was always already in motion, always at the boundary between states, always exchanging with itself at the surface where order meets disorder. Salt did not change ice from one thing into another. It changed the rate of a process that was already happening. It tipped a balance. It shifted an equilibrium that had been running, molecule by molecule, long before the salt arrived. That is not melting. That is something more subtle, more precise, and more true. The surface of the ice was never still. It was never simple. And neither is anything else you think you fully understand.